Hi everyone. Today we're going to talk about parallel paradigms for shared memory parallelism. Now, parallel computation is arguably the most important driver in computational performance nowadays. On modern machines, parallelism occurs on different levels of the architecture. Within a single compute core, parallelism is available through vector operations. We call this vectorizations. On multi-core architectures, each of the multiple cores can perform computations individually and has access to some global memory shared among all cores. We call this shared memory parallelism. Beyond shared memory architectures, parallelism is facilitated by explicitly exchanging data. This can be, for example, by transferring data to and from GPUs or by passing messages between compute nodes using, for example, MPI. We call this distributed memory parallelism. We discussed vectorization and distributed memory parallelism, in particular MPI and GPUs, in other sessions. Today, we look into some general paradigms behind shared memory parallelism. Let us start by introducing some common models of shared memory parallelism. Ages ago, shared memory parallel programs were written with explicit assignment of tasks to threads using, for example, the pthreads library. This is a very low-level approach and is generally very difficult to write a correct program, let alone a performant one. For this reason, the so-called dynamic multithreading approach has become ubiquitous. Dynamic multithreading uses simple constructs to indicate which parts of the program are safe to run in parallel. After that, they let a runtime scheduler assign the work to threads. The programmer interacts with the scheduler rather than with the low-level threading libraries, leading to simpler code with a comparable or even improved performance. We abstract from the actual hardware threads. Nowadays, many dynamic multithreading languages such as OpenMP, SYCL, Intel Thread Building Blocks, Silk, Habanero, and others are available. Some modern programming languages also natively support multithreading, such as C++ since the C++11 standard and Fortran since Fortran 2008. Within dynamic multithreading, we can differentiate between two models of parallelization based on the way the schedule maps the work onto threads. For shared memory parallelism models, we can distinguish between models where threads perform the same instruction, which in this case would be the same piece of the program. The parallelization model is commonly called bulk synchronous processing, data parallelism, or fork join. On the other hand, we may also have threads running through different pieces of code altogether, thus having multiple instructions doing work on multiple data. This model is commonly called task parallelism. Let's have a closer look at both these models, beginning with bulk synchronous processing, or BSP. In BSP, a program runs through 5 conceptual phases. 1. It starts with some code which runs in serial. There is no parallelism here. 2. The code then splits up into multiple threads. Some call this a fork, leading to the alternately used name fork join model for BSP. The threads now, in the 3rd step, compute something in parallel. All threads run through identical code in parallel, but work on different data. These threads are the bulk in bulk synchronous processing. In the BSP model, there is no communication between them in this stage. In the 4th step, once the bulk computational work is concluded, the threads may now communicate and exchange data. And finally, in the 5th step, when a thread completes all its work and communications, it waits at a synchronization point called a barrier for all other threads to finish too. Once all parallel activities have terminated, we fuse all these threads. This is the join in the fork join. Steps 3 through 5, namely the bulk processing, the communication, and the synchronization, are referred to as a super step in the BSP model. In a program, there can be any number of these super steps in a row. To use a more concrete example, consider the following C code where we have some array called data and perform some operations, do something and do something else in 2 subsequent for loops. In the BSP model, we enter the program as a serial code. Before computing the contents of the first for loop, we tell the program to fork several threads to solve them in parallel. Here, for example, we split into 2 threads, with one thread working on the first half of the iterations, while a second thread works on the second half of the iterations. Once they have completed their work, we join them again and repeat the procedure for the second for loop as a second superstep. How exactly the program is told to fork into multiple threads depends on the parallel library or language you use. Some, like OpenMP, will require you to add a directive for the compiler. For others, like SYCL and Intel's thread building blocks or native parallelism in C++ and Fortran, you will need to call a specific function to do so. A great advantage of fork-join parallelism is that it often requires only minimal changes to your program in order to get it to run in parallel and harness the performance of the multi-core hardware. So, it can quickly yield significant improvements. However, it also comes with caveats. Our C code example was quite simplistic. Most importantly, it didn't include any dependencies between the data the threads were operating on. Once such dependencies enter the game, things become much trickier. While there are methods and techniques to deal with them, not all dependencies are easily solved, and it may require you to require parts of your code, or even use an altogether different algorithm which lends itself better to parallelization. A different issue concerns load balancing. Since we have synchronization points at each join, all threads wait there for all others to complete. This means that if we have a situation where one thread needs much longer than the others to do its work, all the others would stand idly by doing nothing during that time. That can easily happen due to some if condition inside the workload evaluating differently depending on the thread's data. Or because we're using an algorithm with an a priori indeterminate runtime, such as an iterative solver, which will reiterate until some convergence criterion is met. Now, a way of addressing load imbalance issues is to reconsider the way in which we schedule the threads. In a previous C example, we split the for loop in half and let one thread perform the first half, while the second thread worked on the second half. But we could have done it differently. For example, one thread could have done all even iterations while the other did all odd ones. Or, instead going element by element, we could split the array in chunks of some size and let each thread grab the first free chunk as soon as it has completed its current work. Usually, different languages and libraries provide several options. There is no generally applicable best solution. The optimal solution will depend on your code and the problem you're solving. To determine the optimal solution, you will need to analyze the performance and behavior of your code. A different parallelization approach is task parallelism. Rather than having all threads run to the same piece of code as in bulk synchronous processing, we can define so-called tasks. Think of them as a sequence of instructions or some unit of work we would like to run on one thread. Importantly, they are not required to be identical. For example, in our C code example, we may define each iteration of the for loops to be a single task. This would look like the BSP approach, where each task performs the same work. But we could also define the first for loop as one task and the second for loop as a second task, which may be solved in parallel. In that case, the two tasks would be computing two completely different things simultaneously. In the second example, a complication of task parallelism becomes immediately obvious. What if we need the first for loop to be completed before the second one may start? Or more generally, what if there are dependencies in our algorithm? Well, in that case, a dependency between the tasks needs to be specified manually by the developer. The precise way task dependencies are specified will depend on the used parallelization language or library. Once a task has no unresolved dependencies, the scheduler can have a thread executed. Upon completion, other tasks depending on the just completed one now may be scheduled and in principle be executed on any available thread. In other words, any idle thread can grab work to do so as soon as it becomes available, thus minimizing their idle time and load imbalances. Now, ideally, tasks are reasonably small. The smaller they are, the more load balancing can be improved by providing threads with enough fine-grained work to be distributed. After all, if we neglect the effects of dependencies, then the maximal load imbalance is determined by the maximal time required for any task to complete. However, the scheduling of tasks comes with an overhead. Making tasks smaller means we will need more of them in total, which in turn means that they will require more administrative scheduling work. Hence, tasks that are too small will result in a performance loss due to the increase in the overheads. So ideally, tasks are also large enough such that the scheduling overheads are negligible. As we have seen, task parallelism offers several advantages over bulk synchronous processing, such as the option to run independent code in parallel and minimize idle time by construction. But naturally, task parallelism has its caveats as well. Writing task parallel code can be very different from writing serial code. So if you intend to parallelize your serial code using task parallelism, it may require a significant effort and rewrite of your serial code. Furthermore, task parallelism requires you to manually specify dependencies between tasks. In complex codes, this may become a challenging problem. Errors in the construction of your dependencies can lead to issues such as incorrect results, race conditions, and deadlocks. We have introduced the two parallel paradigms for shared memory parallelism, bulk synchronous processing and task parallelism, through the source code, namely how we map an existing source code onto threads. But we could also introduce them through the way how they split up work. In this context, if we divide a for loop into segments, like BSP would do, we would call that data parallelism, whereas splitting up work into tasks would be called functional decomposition. Now, having discussed the two most common approaches to shared memory parallelism, let's now have a look at some common challenges which arise when parallelism is involved. We already briefly mentioned the first two we'll look at, namely deadlocks and race conditions. They are dangerous because they can break your code's execution or correctness. Let us begin with race conditions. Race conditions can occur in the sections of the program where shared resources are accessed concurrently. If multiple processes try to modify the same resource simultaneously, the outcomes may be incorrect and unpredictable. To put it in other words, race conditions can occur when the correctness of a program depends on the timing of parallel execution. The threads race for the access to the shared data. When race conditions are present, your results may be incorrect and unpredictable because race conditions violate the fundamental assumption of the program that the current state of data is determined by the instructions being currently executed by a thread. For example, defining a variable int a translates to I need a place in memory for one integer which I will refer to by the label a. From then on, whenever we use the variable a in our code, we assume that the value of a has been set by the instructions we have written and are being currently executed by a thread. However, if a is a shared resource, and in the meantime some other thread has written something into the memory labeled a, then we have a race condition because 1. We do not know when the value of a was changed, 2. We do not know why the value of a was changed, and 3. We do not know what the modified value of a is. So in other words, the value of a has been changed without us or the thread knowing anything about it. Yet we proceed under the assumption that it holds the value that we have assigned it. For this reason, race conditions are generally non-deterministic and not reproducible, making them difficult to track down and debug. To prevent race condition, access to shared resources needs to be protected whenever at least one thread modifies or writes into data. If all threads are simply reading data from shared memory, no race conditions will occur as the data will remain unmodified and therefore correct. There are several methods to regulate the thread's access to shared data. A common way of doing so is to define so-called critical sections or critical regions, which can only be accessed by a single thread at a time. To ensure that indeed only a single thread has access, we need to employ synchronization mechanisms such as mutexes, which are short for mutual exclusion, and locks. You can think of them as a variable specifying whether a resource or critical region is currently free and available or not. Every critical region is then protected by such a mutex or lock. Before entering a critical region, a thread must acquire the respective lock, meaning that 1. The resource must be free, and if it is, then 2. The thread then locks the critical region, specifying that the critical region is currently being accessed. Once it has completed its work in the critical region, the same thread that locked the lock also unlocks it, or it releases the lock, allowing other threads to access it from then on. Aside from mutexes and locks, there are also more sophisticated synchronization mechanisms such as semaphores, which can permit more than a single thread to access to a single shared resource. In the context of scientific computing, a useful example for such a scenario could be a semaphore which permits any number of threads to read some shared data, but to block access for all but a single thread when that data is being written into. Now, attentive viewers may have realized that mutexes and locks must be accessible by all threads in order to work. They are hence a shared resource as well, which therefore also needs access protection to prevent race conditions when the locks are acquired and released. This brings us to a second method of ensuring single-thread access to data, which are the so-called atomic operations. Atomic operations are guaranteed to be performed on an indivisible way, hence the name atomic, indivisible, as if they were a unique machine instruction. This can be realized either through algorithms or through hardware support of atomic instructions. Conceptually, atomic operations are critical sections, but they only ensure exclusivity for a single assignment operations. In other words, they are used only for a single statement such as my variable equals 3. Their advantage is that they have lower overhead than longer critical sections. This makes them practical and attractive for use on single assignments such as locks and mutexes, among many other things. However, the overheads can quickly accumulate when many assignment operations are needed. In such cases, it's preferable to use critical sections. Note that these approaches to resource access protection only guarantee that a single thread has access to a shared resource at one time. They do not specify, set, or guarantee the order in which threads access the resource. To establish a strict ordering of operations between the threads, further synchronization and dependencies between threads and tasks are required. Now that we have introduced locks and mutexes, we can now talk about a common challenge they can introduce: deadlocks. A deadlock occurs when two or more processes are waiting indefinitely for resources that are held by each other. For example, imagine we have two threads, A and B. Say they both need to use the same two pieces of data, data 1 and data 2, which are stored in shared memory. To do so, thread A checks first whether data 1 is available for use, and let's say it finds that it is. So it locks the resource, which means that it marks it as unavailable for other threads to use, but simultaneously, thread B checks first whether data 2 is available. It finds that it is and locks it. Now thread A checks whether data 2 is available and finds that it's been locked already by thread B. Therefore, it sits there and waits for the resource to be freed. At the same time, thread B is waiting for the thread A to free data 1. Thread A and B are deadlocked. They will both wait indefinitely for each other to free the resources they require respectively. As a consequence, your call will effectively halt execution at that point and no further progress can be made. There are various ways to avoid deadlocks. One common method is to enforce resource ordering, which means to ensure that whenever any thread requests a resource, it is done in a specific order. In our example above, the deadlock could have been avoided if both thread A and B had requested data 1 and then data 2 in that order. Thread B would have found that data 1 is already locked by thread A and waited for it to be freed once thread A has completed its work. Another method is to ensure that every thread requests all necessary resources before it begins execution, or, in other words, to avoid the hold and wait procedure threads A and B have been doing in our example. Each thread could first ensure that all required resources are available and lock them one by one before it begins execution. If it encounters an unavailable resource in this initialization phase, it should release all resources it had locked and go do some other tasks. This concludes our section on deadlocks and today's session on shared memory parallelism. Thank you for watching and see you next time.